Okay, sup guys. So today yesterday, I built this machine because actually somebody else was, I think, asking for stuff to do or just trying to figure out something to do. So I told him, hey, just build a Fibonacci machine, just if you want something to do that's easy to get done really quick. So as they were working on theirs, I figured, hey, somebody has like double density adders. So double density adder is this thing is the height of an 8-bit adder. It produces a 16-bit result. Well, actually a 15-bit result, and then a carryout of 16 of a 16th bit. And this one actually was produced by a person named Freya, who is on the server too. So anyway, so I guess I will point out, yes, I used pistons, but that's just because I wanted an AND gate that was 0-tick latency throughput. So like, a block doesn't take any propagation delay to get that signal through, and so the reason I do this is just for clearing at the end when I don't want data in. So I want to show you how this works. Basically, here's an input A and B of the most significant bit, and then here's the bit below that, input A and B, and then the bit below that one is on that side, so it keeps shifting, toggling left and right like that as it works its way down. So Fibonacci is basically, you start with 0 and 1 in a register, and then you add them together, and then you get 2, and then you add 2 and 1 together, and you get 3, and so on and so forth. Well, that's basically what this is doing. Okay, so I guess I'll show you this working. So what I want to do first is I need to preload a 1 in, so I'm going to turn a 1 on, and then I'm just going to place a button here, and clock it like that. And you'll see now, over here, we have a 1 on the output. So every time I clock this button, or I press this button, it's going to perform one operation. So let's do it. So 1 plus 1 is 2, 2 plus 1 would then be 3, 3 plus 2 would then be 5, 5 plus 3 would then be 8, 8 plus 5 would then be 13, 13 plus 8 would then be 21, 21 plus 8, plus 13 would then be 34, 34 plus 21 would be 55, and then you can keep going. You could just keep going. There's 16 bits of this, 16 bits of fun. Okay, so the way you clear it is you come down here, you flip that lever, the pistons retract, and then you need to press this button twice to write both registers. And just like that. Okay, so now let's start with a 1 in there again. Like that. You'll see there's a 1 over here. And what we'll do now is we'll switch this to, instead of clocking it, to coming over here. Like this. So now it'll start the clock for us. So this is going to be a 10-tick clock, so it's going to calculate a number every second. Here we go. And we produce a carryout. So that was 16 bits of Fibonacci ran through an adder that takes 7 ticks of delay, plus a few ticks for busing. So the way this works is, if you see that these two are off at this together, and then these two would be off together at the same time. So every time, basically this clock comes over to this, which is a monostable, which pulses a T flip-flop. So if I click this, you'll see that the T flip-flop is now on, and that forces this to be 1 and this to be 0, and then it inverts the state the next time. So it just alternates between this one and this one, and then those lines alternate between which ones they're going to write, what cells are going to be written to in here, what memory cells get written to. And the output comes, it conveniently is able to be bussed around left and right by this design. So there's a bunch of other double density stuff, but double density isn't very useful because you can't really turn this into an ALU because you don't have access to this carry line. You can't really OR it. You can't really do much with this design. So the one thing that's good for at least is being able to add and subtract relatively easily. So using the setup, I'm adding Fibonacci numbers at 1 Hz. Okay, so here is actually a 4-bit CCA adder, so it's not a double density adder, it's just 4-bit CCA. And I turned this into a Fibonacci machine for somebody who, when I proposed the challenge, they couldn't get theirs quite working too well over here using an insta-carry adder, ripple carry design. This is so much neater anyway than something like that, in my opinion. So anyway, the way this one works is way better, because if you count the ticks, it's 1, 2, 3, 4, 5. We have the comparator, which is 1, 2 on that repeater for 3, 4 there, and 5 there. So when we run this clock, we get a 5-tick clock. What happens here is I will place a button here. When I press this button, on the rising edge, this is going to trigger, and on the falling edge, that's going to trigger. So if I press it, rising edge that goes, falling edge that goes, just like that. Then what I can do is clear everything in here. Like that. Replace my redstone. Change my speed to something that's manageable. Okay, so now that we have redstone placed, now what we need to do is preload a 1 in there. We do that by doing this. Preload a 1 into both registers. So then it's ready to go. It's doing 1 plus 1 is getting 2, and then if we run this right here, it's going to do it at twice the speed of the other one that I had. 5, 8, 13. Yep. And overflowed. So this is much faster because it's less busing required, but it's obviously only 4 bits. So it's really easy to do. So if you guys want to have something to do, if you're bored, build a fib machine. See if you can make like a 16-bit one that's relatively compact and runs at faster than 10 ticks if you can. Anyway, see you guys next time.